Hey everyone, I hope you're having a great week. Today I'm going to be talking to you about low E glass. What is it, how does it work, and give you a little bit of information about the history of its manufacturing.
So I hear people talk about low E glass, but I think very few really understand what it is, how it's applied, and how it functions. What we're looking at here is two pieces of glass. On the left is a piece of low E. On the right is just a piece of regular quarter-inch clear glass. Low E is a thin film coating. So what that means is most times it's metal and metal oxides. Typically that's applied in a couple different layers and it goes right on the top surface of the glass. So the piece on the left, the low E, this one is called our Pilkington Energy Advantage. It's really color neutral, high light transmission, not a lot of color. So you see the comparison to the clear, maybe it's a little bit more reflective, maybe there's a little bit of color to it, but this one's really color neutral, you don't see it. Some low E's are really, really, really colored or really highly reflective. A lot of people assume that low E is a fairly new technology, only been around for a few years. In fact, low E has been around since World War II. During the war, a lot of companies had to help out and actually manufacture products for the war. And what pilots would complain about is they would be up in these dogfights and the windshield would frost up, so they couldn't see out the window. So there was this guy named Harold McMaster, and what he came up with was a way to put chlorine-doped tin oxide on the surface of the glass. It was still transparent, but with this new coating on the surface, it reduces and lowers the emissivity, thus the name low E. What that lower emissivity surface is doing is it's starting to reject heat off of the glass, and that changes the temperature at that which that glass is going to frost up. So again, Libby Owens Ford starts manufacturing low E glass as early as the 1940s to help with the war effort. Really interesting technology and the way that it was applied. However, we really didn't see this take off in the building industry until much later. So, in the late 70s, early 80s, a thing called the U.S. oil embargo came up. It was a big energy crunch. And what happened was, energy prices started to skyrocket. The U.S. says we've got to do something to reduce our dependence on imported oil and reduce our energy consumption. So they do a Pareto chart analysis, which is what you're looking at. On the bottom left there, it shows, how does energy get used in the U.S. About 40% of the energy used in the entire US goes into building operations. So your second level Pareto on the right, well, where does that get used? And the biggest chunks are in lighting, heating, and air conditioning. So what happens is at this point, loads and loads of regulation come in to say we've got to do things to make our buildings more energy efficient. As a result, the regulations around windows essentially said people have to start using double glazed windows and you really have to use low E glass in order to hit these new energy targets. Essentially, there's two different ways to manufacture low E coatings. The first is called pyrolytic coating or hard coating. What you're doing here is in the float glass process in the tin bath, you react gases on the surface of the glass to leave these metal and metal oxides on the surface. Pyrolytic coatings are very hard, very durable. Essentially, the coating is a part of the glass. The other way to manufacture low E coatings is called sputter coating or soft coating. What you do here is you take electrons, you shoot them in a vacuum at these metal targets, and then that metal target leaves metal and metal oxide layers on the surface of the glass. So sputter coatings are softer. If you handle them, they will leave fingerprints. They're a little bit more challenging to actually manufacture. As a benefit, though, the soft coats tend to be better at filtering out the sun's energy. They're more what's we call spectrally selective. So now we have to talk about how low E actually works. You need to think about low E having two primary functions. The first is it acts as a filter for the sun's energy. So what you see on that bottom left is a chart of the solar spectrum. What the coatings are trying to do is take out the UV, filter out the IR, and leave in all the visible daylight. So the very, very first thing that you're trying to do is filter out all the stuff that you don't want that brings in heat, but just let the daylight come in. And what you'll see is about 40% of the heat comes through in visible daylight. So if you look at that little yellow dotted line, that would be a great high visible daylight low E. But what that also means is from an SHGC, a solar heat gain coefficient, about a zero point 0.4, so about 40% of the sun's energy coming in is what you'll get if you have a very, very high daylight product. So if you want a lower than a zero point 0.4 SHGC, you've got to actually reduce your daylight below that 70%, 80% light transmission number. So the first thing that the coatings are trying to do is you're actually trying to filter out the sun's energy. The other thing that you're trying to do is it acts as an insulator. So the way low E coatings function as an insulator is it rejects heat back to its heat source. So if you look at that chart on the bottom right, you see that when the sun's energy comes through, the energy is either going to get reflected, it's going to get absorbed into the glass, or it's going to get transmitted through. And so, from the solar spectrum, what that's doing is the low E coating takes that heat, whatever gets absorbed and whatever it can reflect, it's going to try and reject the heat that comes in on hot days. It's going to reflect more of it, and then what gets absorbed into the glass, it's going to try and reflect that out. The really big benefit that you get from low E glasses in the winter, and essentially what this is doing is long range IR, room heat, is it's actually rejecting that heat and it's moving it from absorbing it into the glass and reflecting it back into the room. So again, low E glass is doing two things. It's filtering out the sun's energy, and then it's acting as an insulator by rejecting heat back to its heat source. So the last thing I'll talk about is practically how does this look. So all of these buildings here have low E. They're very different types. So some are single coated low E silvered, some are triple silver sputtered coatings, some are pyrolytic color neutral coatings. So depending on the type of building, depending on the design that you have, different low E's may have really, really significantly different looks. So you need to make sure that not only does the performance target hit what you want, but the aesthetic and the look of the building need to match with what you're looking for. And this is an example of how that looks in the monolithic glass. So on the left is our color neutral energy advantage, and the middle is an eclipse advantage. So it's a little more silvery, a little more reflective. And then on the far right is that same coating, but it's on a gray substrate. So again, the type of glass that it's on and the type of coating that's there, and then how that's designed into a window, not only does it affect your performance, it also significantly impacts the way that the building's going to look and the aesthetics of the building afterwards. Hope this was interesting to you. If you have any questions, please feel free to send me a direct message, and I'm always happy to help with any glass or glass technology questions that you have. Thanks again, and have a great one.